cannot observe the galactic center in the easily accessible optical wavelength because of dust absorption between us and the galactic center in the plane of the Milky Way. So it took a few years. Initially, you could observe the galactic center at radio waves, where it was discovered, in fact, in the 1930s, then in X-rays, and then in the infrared, where the extinction is not quite as severe. And it was Eric Beckler and Gary Neugebauer at Caltech who, in fact, discovered the galactic center in the 60s. Nowadays, of course, we can make beautiful high-resolution pictures and images, as you will see, in the infrared. That was not possible at the time until the detector, a single detector, stepped on the sky one by one to construct, so to speak, an image. But that was heroic work of the early time. It was clear that in the galactic center there was a very dense star cluster, about 1 million solar masses per cubic parsec, so about 1 million times denser than the local neighborhoods, the solar neighborhood. And of course, that could be the location where one might suspect such a black hole to reside, in the very center. Now, a little later, radio astronomers began to get ever better resolution imagery in the centimeter wavelength continuum through interferometry. So the Cambridge work then led to the VLA, the Very Large Array in the US, and with the VLA, one could have arc-second resolution and construct images like this one here. So this is a 6 centimeter wavelength continuum radiation. That extended emission here is thermal bremsstrahlung, free emission mostly. And then there you see is a very compact source, which is not resolved, Sagittarius A star, which is sort of X marks the spot. And indeed, as you will see, we now think X is it, and we certainly know it's within 0.3 milliarc second of where we think the black hole is. So indeed, these early suspicions were right, and Lynn and Bell got it just right in terms of their proposals. So the next part of the story was to find dynamical traces. Lynn and Bell and Rees had proposed to use hydrogen, H1 and 21 centimeter emission, but that was not very feasible because of the resolution. So really, where things moved in the late 1970s was with Charlie Towns and his group in Berkeley. Towns, Nobel laureate for the laser on laser, had then moved from the East Coast to California and changed from laser physics to astronomy. And he knew about the Lynn and Bell and Rees work. And with his students, I don't have space to show all of them, but some of the more important ones are Tom Jabbar, John Lacey, and others built equipment at 10 microns to look at a fine structure line of neon plus. And the first spectra, which you see here in Doppler space at different positions around the radio source, showed very broad lines, several hundred kilometers per second wide, moving around in Doppler space. So if these motions, these width changes, say anything about a mass, then of course you multiply v squared times r over g, we are completely Newton here, and you get a mass of a few million solar masses. So the early papers, culminating in John Lacey's thesis work, clearly, could pinpoint at that time this mass concentration, and that seemed plausibly in excess of what the stars could provide. It was not, uniquely as an explanation, as Andrea pointed out, because one could have hidden fairly faint stars in the center, including neutron stars, which were known at the time, and make up that mass. But it certainly was a strong first indication. Where to go next? Well, clearly, gas is a somewhat iffy tracer of gravity because it can be pushed around by magnetic fields and winds and so forth, all of which happen in this environment. And so it was clear that one had to go to stars and do stellar spectroscopy. So initially, the field moved the next step, doing near-infrared stellar spectroscopy. And then, over the next 20 years, we have seen an explosion of capabilities. Again, Andrea touched on this. Using the biggest now available 10-meter class telescopes, using images which take advantage of the diffraction limit of these telescopes, not just the seeing limit, which is what usually limits astronomy from the ground. And to do that, you have to have adaptive optics, you have to have laser guide stars, you have to have so-called integral field units, spectrometers, all of which allow you to get down to the 50 milli-arc-second diffraction scale which these telescopes provide in the near-infrared. So that really was the breakthrough. It happened in two places, in Chile with the telescopes of the European Southern Observatory, ESO, here the VLT with 4 8-meter class telescopes, and it happened in Hawaii with the Keck telescopes. So two groups, Andrea and mine, have been working on this project for more than 2 decades. It takes a while, as you will see, to get the evidence to the level we have it now. So here I'm repeating some of what Andrea just already showed. Basically, here's one of these modern images of the galactic center. The cross denotes the position of the radio source, Sagittarius A star. And the initial work basically was patiently taking images at the new resolution, so to speak, to allow us to get proper motions on the sky, velocities on the sky, and just seeing how large they were and whether there was any increase of the velocities toward the center. And indeed, after about 5 years, you could see motions here depicted as 3 different colors in 3 different years. You can clearly see individual stars move. And then analyzing these motions in terms of mean motions, because you don't know the direction along the position along the line of sight, as mean motions or velocity dispersions projected as a function of distance from the position of the radio source. And indeed, you see actually a Kepler law denoting, indicating the presence of a few million solar mass object. Now here already we're talking about a scale of less than a light month. So the mass is about the same that Pounds had in the 70s, but we're going from light years to a light month, and the possibilities in terms of other configurations than black holes already was shrinking, although by no means exhausted. So there were several possibilities, including if you have massive neutrinos, fermion balls, etc., etc. I don't want to touch on these details. Now, the next breakthrough that was clear to both Andreas' group and mine was to get down to individual measurements of gravitational fields from individual stellar motions beyond velocities in order to actually get also the z-coordinate. For this, you need accelerations and, better yet, full orbits. Now, I have to say, when we started with that, it was clear that these orbital periods likely were hundreds of years. So not very feasible in terms of a lifetime of even a Max Planck director, and certainly not within the lifetime of an NSF grant. But we were lucky, and that's certainly not our merit. That's what nature gave us. It gave us objects, stars, which are very close to the galactic center on very elliptical orbits, which are not supposed to be there. And that's a fascinating story, which I will not now dwell on, but Andrea already touched on it, how these stars might have gotten in there. Now, the best star we currently have is this one here, on a very highly elliptical orbit. There's Sagittarius A star. He started in '92. The blue measurements are our measurements. The red measurements are Andrea's measurements. And you see, wherever the two groups measured, they do agree very, very well. Of course, the accuracy got better over time, especially here in this period. And now we are back here in 2015, moving toward the second Perry approach of the star after its first one in 2002. That Perry approach is at 17 light hours Perry distance from the central object, so that's about 3 times the Neptune radius, at which point, moved about 8,000 kilometers per second. Again, v squared r over g gives you what? A few million solar masses. So the same mass which we had seen in all these stages outside is also obviously contained within the central point here. The orbit, as far as we can say, is closed, so it's all contained in a classical central point. There's no deviation so far from good old Kepler motion, highly elliptical as you see, and so that really constrains the number of options dramatically. You still can talk about boson stars if you like, but very little else. Any kind of an astrophysical cluster wouldn't live very long if you managed to prepare the state initially. So for instance, a million neutron stars will live maybe 10,000 years. That's ridiculous. So clearly we are talking about an object which, very likely is a black hole, as long as GR applies, of course, because we have to exclude other states. So that's the current state of affairs. We can measure the mass to about 5%, 4%. Likewise, we can measure the distance to the galactic center through these techniques. We can set a very stringent lower limit on the density of any object which you might have here and is not a black hole. We can say that really nothing else but this central point mass exists. And we can say that the radio source indeed is coincident with the center of mass of these motions to within 0.3 milliarc seconds. So as I said, this is the best case we now have, that this might be a black hole. And you've seen Andrea's movie. You see, I'm showing her version because it's now nicer than ours. She has wonderful PR people at Illinois working with her. And here you see the body of these stars. We, of course, tracking about 10,000 stars in here, but we have about 50 stellar orbits currently, and they all tell the same story. Okay, so that's the story which we can see. I don't, as I said, I don't have time to touch on the fascinating issue how these stars got in there in these very elliptical, isotropic thermal distributions surrounded by this disk of stars. A very fascinating story, but let me just go on from here and now discuss some of the other issues which are raised by this kind of data. Now, Sanjay star, the radio point source. What do we know about it? Well, the radio people have used parallel baseline interferometry at increasingly shorter wavelength to try to image it, which has not yet succeeded, but certainly get the size of it. And the most telling experiment at 1.3 millimeter by Doleman in 2010 has now constrained the size of the millimeter radio emission of Sanjay star to be less than or about 18 microarc seconds. That's interesting because the event horizon size of a 4 million solar mass black hole is 10 microarc seconds. So we are clearly here in a regime of strong gravity. Now, furthermore, some very simple kind of things, of course. The photon orbit, 1.5 times the event horizon radius, would be 25. Okay, so we're clearly very, very close. This is obviously a source which is not yet imaged. So how come it can be so compact? Well, let me say the compactness immediately tells us something about the nature of the object in an indirect way. Because suppose this object is not a black hole, and it's at least that size or smaller. Then, in fact, if you have accretion onto this object, you would get thermal radiation, black body radiation from it, peaking in the mid-infrared, or near-infrared, something like this. This was looked at by Broderick et al., Broderick, Loeb, and Narayan. And basically, from the amount of radiation you do not see, the spectrum of the true spectrum of Sagittarius A star here in blue does not show any excess in the near-infrared or mid-infrared. It looks just like a synchrotron or synchrotron inverse Compton source at all wavelengths between the radio and the X-rays. So there is no thermal radiation bump, which would be there if you have accretion onto a surface, which would then heat up and radiate as a black body. So it gives you obviously a limit on the amount of accretion you're allowed to have on that putative surface, which does not radiate more than that. It gives you a limit. Now then, you can basically calculate the amount of luminosity you would be allowed to get. That turns out to be less than the radio emission. So we are in a situation that the radio emission would have to be something else, and yet you have no accretion onto this object. So here's an indirect piece of evidence. I would not consider it gold-plated by any means that the object doesn't have a surface. Okay? But surely it shows us that the radio emission comes from a region along strong gravity. Now, the interpretation is that this object, if we do get an image, hopefully in the next few years, might look something like this. So we have obviously an inner zone where the material is typically 10 to the 11 degrees. in the virial temperature sense, magnetic fields around 10 Gauss or so, radiating mostly in radio emission as synchrotron, as I said. And so this would be how the object might look like if it were a black hole. So you see here the accretion zone around the object. It's brighter on one side just because in this case it was assumed to be under some angle, so you get Doppler boosting from special relativity. But then, that's the key thing, PR also predicts that if you illuminate a black hole from the back side, there will be a zone, a shadow effect, which is independent of the spin and independent of the inclination in GR about 5 RG. It's about 25 microarc seconds. So the speculation is that this observation here is actually basically, you're seeing the one-sided crescent shape emission from a shadow effect of a black hole. And obviously, if you were able to show that in that image, and you would be able to see the shadow, that would give us a strong indication that we have in a highly relativistic zone around a black hole. Given that we at the same time have a measurement of the mass, and that the ring size here does not depend on spin and inclination in GR, because you have a prediction what the ring size should be. So in fact, forecasts have been done by Johansson and Saltis and others, that by verifying in GR that the two are equal, which can probably be done to about 10% or so, we would have a test of no hair. Okay, we would have a test of no hair with this very likely experiment, which I will come back to. It should happen in the next 2 or 3 years. Another thing the radio astronomers have done is to measure the motion of Sagittarius star itself in the reference frame of background quasars, and then referring that back to the reference frame of the galactic center. I'll give you the details here. And that astonishingly shows that the motion, at least in the direction perpendicular to the galactic plane from Reed and Brunnthaler, is less than 2 kilometers per second. Now remember, the stars, I'm whizzing around here with a few hundred to a few thousand kilometers per second. So if there's momentum or energy equipartition between the stars and that radio source, you can immediately set a limit, at least statistically, to the mass of the radio source now, not the mass around which the stars are spinning, but the radio source. And that turns out to be a sizable fraction. So this is a lower limit, okay? A sizable fraction of the total mass. So indeed, that shows that a significant fraction of that impressive 4 million solar masses must be on scales of strong gravity. Okay, so I think that indirectly pushes the object still closer to where you would say it must be a black hole. So that's the state of the affairs in the galactic center. Now, one thing we haven't yet discussed is the amount of accretion happening in the galactic center, and for that matter, in most nearby massive black hole systems which have been recently studied. Are they quasars? The answer is absolutely no. Most every one of the black holes in the nearby universe is relatively quiescent, and Sagittarius a star at an embarrassingly low level of 10 to the 8 to 10 to the minus 9, the maximum luminosity. So in fact, that immediately tells you the quasar state is extremely rare. And from recent work put together from large surveys of X-ray emitting quasars, the general belief now is that if the maximum Eddington luminosity is out here, that massive black holes spend, even at high redshift, certainly in the local universe, only a small fraction of their time in that state, whilst they spend most of it in an underluminous state where not much accretion into the hole is happening. And the reason for it is very simple. It's all about angular momentum. Okay? It's just so difficult to get material into the horizon when you start with an angular momentum which is 10 to the 9 times greater than what you would have to have in order to fall in. Now, as Andrea pointed out, we did have the privilege and the luck of currently seeing a gas cloud, maybe with a star in the center, or a few Earth masses, which is falling in, and in fact spaghettifying in the most beautiful way, totally disrupting and orbiting around the black hole on a scale of 22 light hours. And this is interesting in this context because it may very well be that this kind of a feeding, which is at very low levels, so to speak, is how most black holes stay most of the time, in that gas clouds and or big stars with an envelope happen to be on a lost cone orbit, get disrupted, and basically the spray of material is slowly dripping into the galactic center. In the case of our galactic center, at a rate of about 1 asteroid mass per day. Okay? Now, the galactic center, there's evidence, was brighter by about a factor of 1,000 a few hundred years ago. So this low state, of course, fluctuates according to this state. So quasars are not typical. Are black holes typical? Well, the study, okay, I've lost here some of my labels. That's again the transfer to this machine. So this is the mass here, along here, logarithmic units of the central mass, black hole mass, versus the mass of the galaxy, which the black hole resides in the nearby universe. So basically you can study, you can look for mass concentrations in many nearby systems now. About 300 or so have been studied. And there's a broad correlation with a very substantial scatter, which we now believe is intrinsic and not just measurement error. The Milky Way, as you see here, is a low mass object. The most massive objects here would be at about 10 to the 9 or even 10 to the 10 solar masses. But the main point is that, roughly speaking, in the galaxy population, where we can do this, about 0.5%, a little less, of the total mass resides in a central object, which, if you believe the galactic center case, is plausibly a central massive black hole. So the question is how this correlation comes about. And as soon as it was found in the late 90s, early 2000s, most everyone speculated it must have occurred in the past. Back when the objects were growing and the quasar state, which was much more typical than it is now. So that the radiation and also outflows from quasars, which we know to occur, can in fact interact with the galaxy around it and may have a strong impact on its evolution. Let me tell you a little more about that story, which again is a story of the last 20 years or so, where we can use, for instance, the Hubble Space Telescope and also ground-based telescopes to make very deep imagery in the optical, rest frame optical, rest frame ultraviolet, but also infrared waves and so forth, to look back in time by looking out. And thereby, basically charting the activity of stellar formation, and that is galaxy formation, as well as the activity of black holes. And the story which emerges from this is summarized in this plot here. So this is redshift from our current position back in time, or here, look back time from our current position back in time to the Big Bang. And so you see here, everything is relatively quiet, and as you go back, star formation rates, summarized by this black curve and the very many measurement points here, increases by about a factor of 20 to time about 10 billion years ago. You could call that period the galaxy formation time. That was the time when, for the first time, the big dark matter halos were collapsing and bringing baryons in at a very high rate. Star formation rates were very high at that time, mainly because there was so much gas around. Half the baryonic material in galaxies was in gaseous form, so you could form stars at a very high rate. That is not the case now. The Milky Way produces one sun per year, whilst a Milky Way-like mass object back then would have done 20 times, 30 times that much. So you see, this is the so to speak, the end time of the galaxy formation epoch. This time here, back to the Big Bang, is a time when you basically had to first assemble the halos, which then allowed galaxy formation to occur. So that's the galaxy side of the story. The black hole side of the story is summarized in blue and green, basically mapping out the activity and abundance of quasars with X-rays, radio, other techniques. And it's remarkable how well the two track each other. with a Herschel satellite looking at far infrared emission as a very robust probe of star formation versus X-rays, you can then actually here in this peak period measure the relative luminosity of X-ray emission from a accreting black hole relative to the star formation rate in individual galaxies and then average over the galaxy population in these redshift bins. And you can see that the ratio in terms of accretion rate is about 0.01 or so percent. So that's close to the ratio of the black hole mass to the galaxy mass in modern times. So this we call coevolution, and this shows that these big black holes were growing. I'm not saying they were created, but they were growing at a very fast rate at a time when also the galaxies were forming. There's of course intense discussion and studies how that could occur. Until recently, the dominant channel was thought to be major mergers, because in the early redshift high density universe, the probability of two galaxies to actually make an inelastic interaction leading then to the buildup of a yet bigger system in a different form, so from two disk galaxies to a more spheroidal galaxy, was fairly frequent, about once every 3 or 4 gigayears per galaxy. But now we believe actually the more likely dominant channel is actually internal galaxy processes where galaxies get gas from the intergalactic dark matter web, cosmic web, and basically because friction was very much higher at that time because of the high gas fractions. Gas was brought inwards very efficiently and perhaps then allowing black holes, which were already had formed earlier, to then grow very rapidly. So the story seems to emerge that galaxy evolution and black hole growth went almost lockstep, at least average over long times. Remember, of course, in short times, the variability rate and the accretion rate of black holes varied greatly. But of course, we still don't know now when the black holes, the sea black holes, that's a big problem. I'll come back to this next. So then galaxies grew very rapidly in that period, doubled their mass every 600 million years or so. Yet we know that galaxies, star-forming galaxies, at all redshifts, we can do this now, redshift 0 in the local universe all the way to 10 gigayears ago, live on the so-called stellar mass star formation rate sequence. And so the belief is that the galaxies grow along this sequence. So they grow in mass by forming stars, consuming the gas which they're getting. But at some point, you see, there is no more. So they stop all growing at a mass of about 10 to the 11 solar masses. So here are different mass curves in these different redshift bins, and they all are exponentially cut at the so-called Schechter mass of 10 to the 11 solar masses. So what stops the growth of these galaxies? What makes galaxies, so to speak, no bigger than 10 to the 11 solar masses? So obviously there have to be processes which bring galaxies from here to what we call the red sequence down here, where passive elliptical galaxies are located. Now there are two favorite mechanisms. One is one which already was discussed by Rees, Ostreich, and others in the early times, recognizing that when you have baryonic gas falling into a halo, you get a shock front which heats up the baryonic gas to a temperature equivalent to the virial temperature of the halo. And if that gets above a few million degrees, the cooling of intergalactic material is very inefficient. So very massive halos are just not very efficiently cooling their baryons, and therefore the accretion rates are low. The second one has to do with perturbations, major mergers, but also disk instabilities in the galaxies, basically perturbing the galaxies, and perhaps at that time, as I described just before, feeding their black holes very efficiently. And when the black holes are fed, they tend to produce outflows. In fact, in a study which we are just currently completing, we have been able to show that star-forming galaxies, not active galactic nuclei, but star-forming galaxies 10 billion years ago, show at a very high rate above near the Schechter mass and above, very broad emission lines indicative of these outflows. So that may very well be, so to speak, a very significant piece of evidence in favor of AGNs being, so to speak, the regulator of the most massive masses galaxies can attain. But certainly it shows that these massive black holes, not only are they common, but they're also very important for the evolution of galaxies. Two more issues before I come to my last point. One is the one I already mentioned, namely the issue that in the end it's all angular momentum. That factor of 10 to the 9 is vicious if you want to form a black hole and make it grow. So you have to really do major damage to galaxies in order to get a gas down the throat, and I discussed various possibilities already. The second one is what we call the seed problem. So if you grow black holes at the maximum Eddington rate, then if you start with a seed mass at T0 equals 0, and then you go to a final mass, the time which it takes to grow is about 200 million years times this log factor. Now if the seed would be, say, plausibly a stellar type black hole, which you could have formed in the early universe through the collapse of a very massive star, that might be 100 solar masses here, and you end up at 10 to the 9, then this log factor is about 15, and so that number here is several gigayears. However, we do see some black holes of that mass already about 800 million years after the Big Bang. So there are some issues here which, of course, need to get resolved. It's only a small fraction of such massive black holes at that early time, but still, we would like to understand how early were these black holes formed, and was it a stellar seed, or was it a cluster seed, or how did that happen? I don't think that we are considering very much primordial black holes, but in Paul Steinhardt's model of, oscillating universes, well, maybe you could have taken some with you from the last universe and then you shove it into the new universe. Okay, let me finish then with the future, in particular vis-a-vis GR. So the astrophysical story is exciting to many of us, but of course perhaps for you the more important question might be whether we can use these things, and in particular the Galactic Center, for studies of general relativity. The answer hopefully is a resounding yes. So several things can and will be done. We are currently in the stages of commissioning an instrument, very ambitious instrument, of turning this 4-telescope array into a single telescope. A single near-infrared telescope, 120 meters in diameter, through interferometry. So that would allow us to go from 8 meters in resolution to 120 meters in resolution. That's a factor of, it's not actually 120 over 80 as you might think, because interferometry actually has twice the resolution. So it's certainly a good factor of 20. And so we've developed over the last 10 years an instrument which I shall describe in the next slide, gravity, to do 10 microarc-second imaging astrometry in the Galactic Center to, in fact, testing GR with stars, but also with gas. The big telescopes of the next generation would also do some of that, although it will take another 10 years or so until they come into fruition. Very importantly, the VLBI community is getting ready to image the black hole, not just measure its size, but image it. And of course, I described already the goal of seeing that shadow, which really would be a tremendous step forward. And then finally, already discussed on Monday, if there are any pulsars in the Galactic Center which can be used as clocks, would be fantastic. People have looked for 40 years, have not seen a pulsar until 2 years ago, and that pulsar turned out to be a very unusual object which cannot be used as a clock. But it encourages everyone in the radio community to go look for it. I don't know, Bruce, whether you're involved in going through the data, but that's kind of goal which is really there. So a few more words about our machine. So we are building, what is a dual beam astrometric interferometric imager, a very complicated word. The trick is because you have to go deep in order to see faint objects. At the same time, of course, the Earth atmosphere disturbs the interferometry greatly at a kilohertz rate, so we have to actually separate the detection of the fringes on a bright object from the study of the galactic center itself. So we are basically measuring the phase difference between two objects. And then the third thing is you need to use adaptive optics on this object here to coherence the big telescope. So it's quite a bit of gymnastics to get to this, but in the end we want to do 10 microarc second astrometry. There have been major innovations in instrumentation here, like integrated beam combiners, no noise detectors, 5 nanometer metrology, and so forth. No, that's 2 microns. It's 2 microns. 10 microns is a very bad spot to work at because it's so much thermal noise. We want to look at the stars, and so that's 2 microns is the. So the machine is currently on the mountain in Chile. We've done our first commissioning very successfully, demonstrated already the first key criteria of the instruments. It will take us about a year to calibrate it and then get onto the galactic center. So we're quite hopeful that we will get data. So the plan for these various tests is a bit like this. It's going to be sort of a stepping stone where the easy stuff, maybe not of the greatest excitement for you, which is certainly post-Newtonian first order things like gravitational redshift from the Doppler motions. When S2 goes into its next parry, Andrea described that, that's very likely to occur for both teams. The next one will be detection of the Schwarzschild precession term for S2. That we can forecast, and we are fairly sure we can see it with good sensitivity in about 4 or 5 years. Whether or not we can see the spin from lens steering depends on whether or not there are stars on still closer orbits. That we don't know. So that we will know whenever we make the first image of the galactic center next year. And then the shadow experiment I mentioned would give us, together with the stars, a shot at no hair. There may be more advanced things we can do, as Cliff Will has described. If we have several stars in the lens steering regime, so to speak, so that we can separate the quadrupole and frame driving terms. But that's for perhaps generations beyond my time, if it comes to that. But the Galactic Center has so far always delivered enormously well, and we'll see how that continues. Thank you.
Thank you very much for an exciting talk. May the Galactic Center stay with you.
Yes.
We have the time for a few questions. If not, remember there will be half an hour question, but Bruce,
suppose that somebody was skeptical about black holes. So for example, you showed that from looking at the orbit of S2, you come within 1,400 Schwarzschild radii. We know what the mass is. So the mass is certainly concentrated in there. What are the other, if you were trying to convince a skeptic, how much closer could you get from the different data? I was trying to always turn it to Schwarzschild radii and it didn't succeed. So can you tell me what the numbers are? What's the closest evidence?
What I call the lens steering regime would be 100 to 200. It would still be substantially outside the region. So it will just be far.
But you're not there yet, is that right?
No, because
so that's just based on the current data, on the data you currently have. What's the closest?
So what we currently can do with the radio astronomers, we can look at the inner multiplication zone, where there is this hot plasma, which presumably is orbiting. It's not a clock, because it's not gravitationally bound. And so to see sort of a revolving spot, which we could in fact do, is highly unlikely, but we will have to see. Likewise, what are the radio